Hey everyone, I want to talk about something that 90% of people working with AI are completely overlooking right now, but it might just be the most important development we've seen this year. Google just dropped something called embedding Gemma, and while the name sounds about as exciting as watching paint dry, this little model is quietly reshaping how we think about AI deployment. Here's the thing that got my attention immediately. For years, we've been stuck in this impossible choice when it comes to text embeddings. You either pay through the nose for OpenAI's API and send your sensitive data to the cloud, or you download some massive open source model that eats up your GPU memory and runs like molasses on your laptop. Google just said, forget that trade-off, and built something that changes the entire game. Embedding Gemma weighs in at just 308 million parameters. To put that in perspective, that's smaller than GPT-2 from 2019. Your first instinct might be to dismiss it as too small to be useful. But here's where things get interesting. This tiny model is absolutely demolishing everything else in its weight class, and even punching way above it. On the MTEB benchmark, which is basically the gold standard for measuring embedding quality, it's sitting at the top of the leaderboard for any model under 500 million parameters. But size isn't the only story here. The real magic happens when you look at what it can actually do in practice. This model runs in under 200 megabytes of RAM. That's not a typo. While other comparable models need 2 to 4 gigabytes just to load, embedding Gemma sips memory like it's on a diet. I've been running it on my phone, and it genuinely feels like having a superpower in your pocket. The speed is equally ridiculous. On Google's Edge TPU hardware, it can generate embeddings for a 256 token chunk of text in under 15 milliseconds. Compare that to OpenAI's API, which typically takes anywhere from 50 to 200 milliseconds depending on server load and network latency, and you start to see why this matters. We're talking about the difference between something that feels instant and something that has just enough lag to break your flow. Now, you might be thinking this sounds too good to be true. Small models usually mean sacrificing quality, right? That's where Google's engineering really shines through. They didn't just shrink an existing model and hope for the best. They rebuilt the architecture from the ground up for this specific task. Instead of using the typical left-to-right reading pattern that most language models use, embedding Gemma employs bidirectional attention. Think of it like the difference between reading a sentence word by word versus taking in the whole sentence at once. For embeddings, this is crucial because the meaning of any word depends on everything around it, not just what came before. They also implemented something called Matryoshka representation learning, which sounds fancy but is actually brilliantly practical. Instead of training separate models for different vector dimensions, they trained one model that can compress its output from 768 dimensions down to 512, 256, or even 128 dimensions without losing much accuracy. This means you can start with full quality for testing, then compress for production to save memory and storage. Let me give you a real example of why this matters. Hugging Face recently took the base embedding Gemma model and fine-tuned it for medical applications using a dataset called Myriad. They used a standard RTX 3090 gaming card, spent 5.5 hours, training with about 100,000 examples, and watched the accuracy jump from 0.834 to 0.886. In the embedding world, that's like going from good to exceptional. What's even more impressive is that this specialized small model ended up outperforming much larger general-purpose models. It's proof that focused, domain-specific optimization can beat raw scale every time. And the best part? That whole fine-tuning process cost maybe $50 in electricity and compute time. But let's get practical for a moment. When should you actually use this thing versus the established alternatives? I've been testing it across different scenarios, and the patterns are pretty clear. If you're dealing with sensitive data that can't leave your premises, embedding Gemma is a no-brainer. I worked with a healthcare startup recently that was spending thousands monthly on OpenAI's API just to embed patient notes for their search system. They switched to embedding Gemma, running on a single server. And not only did they eliminate that monthly bill, but their search actually got faster because there's no network round trip. For high-volume applications, the economics become compelling fast. OpenAI charges about 2 cents per million tokens. If you're processing more than 10 million tokens monthly, which isn't hard to hit with any serious application, running embedding Gemma locally starts looking very attractive financially. The mobile story is where this gets really exciting. I built a demo app that can search through 10,000 personal notes in under 100 milliseconds, running entirely on an iPhone. No internet required, no data leaving the device, and search quality that rivals what you'd get from a major cloud service. That's the kind of capability that opens up entirely new application categories. Of course, nothing's perfect, and embedding Gemma has its limitations. The context window is capped at 2048 tokens, which means longer documents need to be chunked manually. Some specialized domains might need fine-tuning to reach optimal performance. And if you need multimodal capabilities combining text with images or audio, you'll still need to look elsewhere. But here's what I find most significant about this release. It represents a fundamental shift in how we think about AI deployment. For the longest time, the assumption was that the best AI capabilities would always require massive computational resources that only big tech companies could afford. Embedding Gemma proves that's not necessarily true anymore. The ecosystem support is already impressive and growing fast. Llama lets you install it with a single command. LM Studio provides an intuitive interface for testing. Llama CPP compiles it into optimized versions for different hardware. Apple's MLX framework makes it run smoothly on Apple Silicon. And for web developers, Transformers.js lets you run it directly in the browser with no server required. What we're seeing is the democratization of AI capabilities that were previously locked behind expensive APIs or required significant infrastructure investment. A college student with a laptop can now build applications with semantic search quality that rivals what Google uses internally. This trend extends beyond just embeddings. We're entering an era where the choice between cloud and local AI isn't about capability anymore. It's about specific requirements around privacy, latency, cost, and control. Embedding Gemma makes the local option significantly more attractive for a huge range of use cases. I've been running some calculations on the total cost of ownership, and the numbers are striking. For a typical RAG application processing 1 million queries monthly, OpenAI's embedding costs alone would run about $200. Add in the costs for the generation model, and you're looking at $500 to $1,000 monthly just for the AI components. Running equivalent functionality locally with embedding Gemma paired with a quantized Llama model costs essentially nothing after the initial setup. But cost isn't the only consideration. There's something profound about having AI capabilities that work offline, that don't depend on internet connectivity or external services. I was on a flight last week testing a prototype that could analyze and search through a collection of research papers using nothing but the laptop's local processing power. That kind of reliability and independence feels increasingly valuable in our hyper-connected world. The privacy implications are equally significant, with growing awareness around data security and regulations like GDPR. Being able to process sensitive information without it ever leaving your control is becoming less of a nice-to-have and more of a requirement. Embedding Gemma enables compliance-friendly AI applications that would be difficult or impossible with cloud-based services. Looking at the competitive landscape, Google's positioning here is smart. They're not trying to kill their own cloud embedding services. Instead, they're expanding the total addressable market by making AI accessible to use cases that were previously economically or technically unfeasible. It's the same strategy that made Android successful, providing a high-quality open alternative that benefits the entire ecosystem. The technical execution is impressive too. The same tokenizer used in Gemma 3 ensures compatibility when you want to pair the embedding model with a generation model for RAG applications. The weights are available under the permissive Gemma license. And Google even included practical documentation with ready-to-use examples rather than just academic papers. I think what excites me most is how this changes the innovation landscape. When AI capabilities require significant infrastructure investment, innovation tends to concentrate among well-funded companies and research institutions. When you can run state-of-the-art embeddings on a phone, suddenly anyone with an idea can build something meaningful. We're already seeing early examples of this democratization effect. Indie developers are building personal knowledge assistants that work entirely offline. Researchers in developing countries can analyze large text corpora without expensive cloud bills. Privacy-conscious organizations can implement sophisticated search and recommendation systems without compromising their data governance principles. The fine-tuning story is particularly compelling. Because the model is relatively small and efficient, the barrier to specialization is much lower. That medical fine-tuning example I mentioned earlier required just a few hours on consumer hardware. Compare that to fine-tuning larger models, which often requires days or weeks on expensive GPU clusters. This accessibility of customization means we'll likely see an explosion of domain-specific variants. Legal embeddings trained on case law and contracts, scientific embeddings optimized for research papers, financial embeddings that understand trading terminology and market dynamics. Each of these would have been prohibitively expensive to develop with larger models, but becomes feasible with embedding Gemma as a starting point. The model architecture choices reveal some deeper insights about the evolution of AI. The bidirectional attention design shows that Google recognized embeddings are a fundamentally different task from text generation, requiring different architectural solutions. The Matryoshka approach demonstrates that efficiency and quality don't have to be mutually exclusive with smart training techniques. These innovations suggest we're moving beyond the bigger is always better phase of AI development toward more nuanced, task-specific optimization. Embedding Gemma might be a preview of a future where we have specialized, efficient models for specific tasks rather than trying to solve everything with massive general-purpose models. The implications for edge computing are profound. As IoT devices become more powerful and AI inference chips become more efficient, having models like embedding Gemma enables intelligent behavior in places where cloud connectivity is unreliable or impossible. Imagine autonomous vehicles that can understand and search through their manual and diagnostic information locally, or industrial sensors that can classify and analyze their data streams without network dependencies. From a strategic perspective, this release positions Google well for the next phase of AI adoption. As organizations move beyond experimentation toward production deployment, concerns about cost, privacy, and reliability become paramount. By providing a high-quality local alternative, Google is ensuring they remain relevant even as customers seek to reduce their cloud dependencies. The broader industry implications are significant too. If small, efficient models can match or exceed the performance of their larger counterparts for specific tasks, it challenges some fundamental assumptions about AI development and deployment. We might see increased investment in optimization and specialization rather than just scaling up model size. For developers and organizations considering their AI strategy, embedding Gemma represents a new option that didn't exist before. It's not necessarily better than cloud alternatives in every scenario, but it expands the solution space considerably. The key is understanding when local deployment advantages outweigh the convenience of cloud services. The success of embedding Gemma will ultimately be measured not just by benchmark scores or download numbers, but by the applications it enables. The real test is whether it empowers a new generation of AI-powered products that couldn't exist before because of cost, privacy, or infrastructure constraints. Based on what I've seen so far, I'm optimistic. The combination of quality, efficiency, and accessibility hits a sweet spot that could unlock significant innovation. It's not the most powerful embedding model ever created, but it might be the most democratically accessible one, and sometimes that matters more. The future of AI isn't just about building more powerful models. It's about making AI capabilities available to more people in more contexts. Embedding Gemma takes a significant step in that direction, and I suspect we'll look back on it as a turning point in how we think about AI deployment and accessibility. The question isn't whether local models will completely replace cloud services, because they won't. The question is how the balance will shift as local options become more capable and the integration between local and cloud becomes more seamless. Embedding Gemma suggests that balance is shifting faster than many people realize. What do you think? Are we headed toward a more distributed AI future where capability is spread across devices rather than concentrated in data centers? Or will the convenience and continuous improvement of cloud services maintain their dominance? The answer probably depends on your specific use case, but having more options is always better than having fewer. And right now, we have more options than ever before.